So now we will discuss about the other boundary condition also. We will include the other boundary condition. That means now our system will have two pegs at two ends. Okay. Now, and in fact, this is more of a practical problem than the other one, because you will never be able to create such a system of semi-infinite string sort of. I mean, you have to do a lot of extra work to actually create such an experiment. But this is a very practically available experiment which you can always do. That's why this is the most important aspect of the discussions which we have till now. Okay, now here if you remember the left side and the right side, earlier because we were not having the physical string on the left to the peg, we were having an imaginary string to the left of it. So now we will have similar things onto the right of this also, because now we don't have the physical string to the right. And one observation you should make, that whenever say a profile of shape comes and hits this, we saw that it flips and exactly the same shape reflects back, right, on left side peg. And now suppose this length is say L. Okay, that means just try to follow a wave which has just now reflected back and started moving this side. So it will take how much time to reach there? L over C, right? So time is say L over C to reach that point, and the same thing will happen there. It will again be reflected back both phase wise and shape wise and come back. Now by the time it reaches here, again it will take what, T1 time or T2 time, which is again L over C. Sorry. Right. But when it comes here, by that time it would have got exactly the same shape by now, right? Means when it went there and came back, and it is again going back for the second time. So it will be exactly the same as it was at the beginning, the shape wise. So that's why these kind of system will always have a periodicity in their what do I call motions. So as soon as you fix two ends like this, you will have a periodicity, because after this time this thing again will repeat. After every such L, 2 times L over C, if I call it 2 times L over C, okay, after every such a time, same thing will start happening here. Okay, and that's why sort of periodicity is inbuilt to this kind of system, and this is very much in a way different, or in fact contradictory to the one which we had seen with even the simple 2 DOF system. You remember, in the 2 DOF system, to have a periodic motion was very rare. We said that when omega plus and omega minus, only when they are integral multiples of each other can there be any periodic motion. Other than that, always it will be aperiodic. So mostly it was aperiodic, but here always it will be periodic. We will actually show that it is going to be periodic. Okay. Now for that, what we will do is, again as the solution, we will say we take say f x minus ct, sorry, so this was going rightward, and plus say minus x minus ct. So that was our reflected wave, right? There was a minus maybe here, otherwise it won't get cancelled, no? When it got reflected, only when one side of boundary was there. So this is what we had as our solution, right? Now because we have one more condition now, that means at x is equal to L, again y needs to be 0. So you just see here, if I put say f L minus Ct now has, if I put this to be f of minus L minus Ct, if this condition is satisfied, if I choose a function such that if this condition satisfies, then this will become 0 because of this minus. So then I am done. So this is an additional condition which is coming from the fact that at x is equal to 0, x is equal to L, y has to be 0. Now if you think now just think that f of z is equal to f of z plus 2L sort of. If you add 2L, if z is x minus ct sort of, that means you have a periodicity of, this is a periodic function of 2L length. How it will look like is, I will draw in the other page because it's so suppose this is, I will draw a small one, and this is the actual physical portion of the string. Then suppose here I will draw say like this. Then here I will draw another at L maybe. Now here exactly it will be like this, that is required for the left hand condition, and this side it will again be the same like this. Here there is a peg, and from there it will be like this. That means here it's moving this side, 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 and this is of 2L. So if you take this to be the complete solution on from z equal to minus infinity to plus infinity. So, that will satisfy the condition of the complete wave equation plus the boundary condition on this physical domain. Okay. That means you can consider any part. Means if you think this part is okay with you, so this is again also 2L. So this full thing is getting replicated there. So the same function repeats every 2L length. That's the requirement for this also to be satisfied, which we got like this. Okay. And the way we were defining always in terms of initial condition, initial shape and initial velocity profile, the same way we can define, that's a long, I'll just write down maybe. Just if you want to code, you can just use this to code it. Okay. Now the y x t, as usual, half of, I think we had written h x minus c t plus h x plus c t minus 1 over c q x minus c t plus 1 over c q x plus c t. Okay, so that's the general solution where you define say h z to be, here it's a bit, first you write like this, say from say z is between say 0 to L. So that will be obviously y naught z, because that's what you have defined, the initial displacement condition. Then if you go say z is from minus L to 0, you will have what? Minus y naught of minus z. Just try to see this part. So I'll just write 0 to L, this is minus L to 0, this is L to 2L, this is 2L to 3L. Okay, so this is, suppose, is y naught of z, so you are defining like that. See, the sometimes it comes to your mind that why are we writing like this? This is because this part is defined only for the physical domain where physical string is available, but our function has to, we are trying to define it from minus infinity to infinity, and that's why we are defining it like this, so that once you apply this to the domain 0 to L, you get the solution. Okay. And once you go from z is from L to 2L, you get yeah, so minus this, so 2L minus z, and for 2L to 3L you get y naught z minus 2L. Yeah, so this is one, and I think the qz thing you can write as, again we have that thing, so v naught u du integral from 0 to z is s z, this anyway is true. And in terms of s, we will now define, so s of z is between this 0 to L, and S of minus Z from minus L to 0, then S of 2L minus Z from Z L to 2L, and S of Z minus 2L from 2, 3L, and in fact I don't have space. This thing just go on like that and go on like that. Similarly here it goes on like that, it also goes on like that. Okay. So these are, so here I wrote Q, no? Yeah, that's fine. It's in Q. These are okay. So now once she shares the codes, at least from there you can move it forward to incorporate these things for both the boundary conditions, because that same code slightly has to be modified in this, because once you see it, if possible, for me it's not possible to draw that, otherwise I would have drawn and shown that how it looks like for a given condition, but it's impossible, very complex. Okay.